Professor Velukar, Professor Dhande, Professor Kothari, friends, it's a great pleasure to be here this morning. Professor Velukar and I together had the torture of traveling through New Zealand, 8 universities in one day. And during that time when we were going around and talking, he mentioned this lecture series to me. It was an idea in his mind, and when he invited me to come here, I was more than happy to accept. Even though it is unusual to have lectures like this on a Saturday, I think it's a very good idea to have some sort of free-for-all, somebody's cell phone here, some general lectures on different topics. Okay, all right. So I was pleased to do this. What I'm going to talk about today is a topic which, as I looked at the audience, I recognized some familiar faces. So I am sorry that some of you will have to hear it again. This is about the subject that I study and I've worked on for the last many years now. It's on chaos theory. The title was really not meant to be provocative, although as Professor Velukar pointed out, there's one part of it which we are very good at doing, which is just getting the chaos out of order. But this is really more about the other part of it. The heart of the question, really, that I want to pose to you all today, and this is true in many areas of science and as well as in the humanities and social sciences. We are, as it were, surrounded by phenomena which we try to make some sense of. That's much of the purpose of why we are here, or what we do when we are here. And we are confronted with two types of basic phenomena, some which are easy to predict and some which are not. Of the kind which are easy to predict, most of the time what we do is to create patterns and try to observe these patterns. Once we've got these patterns, we try to extend these patterns and so on. Let me try to move a little this way so that I can see as I move along. Okay. Some of these patterns are in space, and some of these patterns are in time. And temporal phenomena like the rising of the sun or the setting of the sun, these happen every day like clockwork. So after a while, it gets quite easy to predict when the sunrise or the sunset is. Other patterns are patterns in space, and again, surrounded by a whole wealth of beautiful patterns. And the point of it is really that once you know the arrangement to some level, you can try to predict what the arrangement further on is going to be. Some of these patterns are repetitive, and some are not. And these form, to a large extent, the basis of our understanding of a problem. Sometimes it gets put in mathematical language, sometimes it comes into behavioral stuff. But most of the time, our understanding, in as much as we understand things, is really based on observation, systematization, and then extending from there. Now, I'm going to give examples of stuff which is not quite so easy to predict. But as we have been looking at various types of phenomena, our grappling with phenomena that are not predictable has become a little better. We are able to understand why certain phenomena, especially in time, are irregular in the sense of being unpredictable. And what this lecture will be about is really to try to understand what are the consequences, how does this come about? How do you have a system, or how do you have a phenomenon that is not easy to predict? And why is it important? There is a phone call. Why is it important? And what are the properties of any system, or what are the properties of the phenomenon that make it either regular or irregular? Okay. Now, where would one ask this question? It turns out, and this has been true for in the last 30, 40 years, people have been asking this question now for a very long time in various different aspects of the sciences particularly, but also increasingly, as Professor Velukar pointed out, in the social sciences. In a sense, historically, the first time this was asked in a public way was by the King of Sweden in the 1880s, who posed this very important question for a prize. And this prize, which was won by a mathematician, Poincaré, gave rise to a sort of burst of activity. In fact, it founded this subject. The question that he asked was, is the solar system stable? And to some extent, what this means is, we know that we've been going around the sun we've been going around for about 4.5 billion years now. So 4.5 billion times we have been going around the sun. Would we always be going around the sun? Will this go on forever? If we were not precisely in our orbit, could we be in any other orbit? So, and we have only one moon. What would happen if we had a few more moons? We know that we have 9 planets, or 8, depending on how you look at planets. If you have only 8 or 9 planets, is this the only stable configuration do we have, or are there others? So this is a question that was asked in a sort of very general way, and the answer, it turns out, is that the solar system is not very stable. But more about that later. All of us in this room have a heart. Most of the time it's beating quite regularly, and 60 times every minute, or somewhere like some number like that. But we also know of situations and when people undergo heart attacks. So it's not as if the heart continues to beat regularly all the time. There are certain times when it doesn't. So the question is, what happens? Is it beating faster, slower? Does it stop being periodic? This is a major question, and you'll have undoubtedly heard of words like cardiac arrhythmia. So the rhythm is broken, the arrhythmia is not being regular, not being periodic. So the question of what actually happens in a heart attack is of great interest, and that also comes under looking at irregular phenomena. The list can keep going on, particularly because we are surrounded by phenomena of this kind. The question of whether something is predictable or not, actually, many ways people have thought about it, but one of the most eloquent was Einstein, who, in a discussion on quantum mechanics, actually said what's quoted over there. And he says that I, at any rate, am convinced that God does not throw dice. Namely, that God does not, or that somehow that the natural world is not particularly given to probability or given to chance. What's been happening in the last so many years is actually the feeling that God does, in fact, play dice. And, it turns out that even very simple systems can behave almost as random as a coin toss. The coin toss is, after all, the one phenomenon that we all appeal to whenever we want something to be equiprobable, because we believe that if the coin is fair, it will fall either heads or tails with equal probability, and furthermore, that you cannot predict. If you throw the coin well enough, you can't predict precisely whether it will fall heads or fall tails. So the coin toss is some paradigm of unpredictability out of these two options. Also unpredictable is precisely how the slideshow works. Okay. Yep, that one. Thank you. All right. Okay, so these issues of predictability, unpredictability, of regularity, irregularity, all these have found some resolution in what's called chaos theory. And what I try to do in the remaining 40-odd minutes of this lecture is to give you just an introduction to what this is about, and perhaps, just point out some of the ways in which these questions are important and where they might occur in your areas of study. The formal area which this comes under is the study of nonlinear dynamical systems. And the coin is a very good example of a nonlinear, it's a dynamical system because it's moving in space and in time, it's flipping around, and it's nonlinear because most of the world really is. Okay. One of the reasons why the subject has also been very attractive is, first of all, the terminology. Words like chaos and order, we feel we understand them, and they also describe so much of the world around us in some very evocative way. There was a very important book that contributed to the subject's popularity. It's called Chaos: The Makings of a New Discipline, The Making of a New Science. It was on the bestseller list for years and years, and that, the way in which this was discovered, all this has got a little romance attached to it. Many of you would have seen this image because it's the root of many screensavers. So even if, the subject itself has not impacted you in any other way, it's impacted computers and computer screens. And all these are ingredients of the chaos theory story. These kinds of patterns which come out of chaos theory find some mimicry in nature, giving rise to the feeling that perhaps there is the same kind of mathematics that underlies both natural objects as well as this interesting discipline. So, to give, without further ado, what's a good example of these kinds of phenomena? There are some natural phenomena, such as the times of the sunrise or the sunset, which are archetypical examples of what is predictable. If you open the newspapers, every day they will tell you to the last minute, and if you wanted really, you could go down to the last second, the time of the sunrise, the time of the sunset. And if you live in South India, you can also hear about Rahu Kalam and other such things which are, all part of the unpredictable phenomena, but still. So you have the times of sunrise, sunset, everything told out, or the times of the eclipse. There's a website. You can go on there, and I did this about a year ago. For the city of Hyderabad, you put in the latitude, longitude, and out comes the details. As I said here, one of these is I don't know. Anyway, as you can see on the screen there, on this 26th of February last year, the sunrise began at so and so, ended at so-and-so, and moonrise and so on. Okay, so this is well known. We see it every day, and we know that we can, in fact, predict very well these kinds of times. Now, one of the things that I was interested in, and this I was doing in the year 2008, I was told that there's this wonderful eclipse that was going to happen in 2009. It was the great eclipse of 2009. And I don't know how many of you in this audience are interested in eclipses, or I had never seen a solar eclipse. So I decided that I wanted to go and actually see this eclipse. A year or more before the time of the eclipse, this map was already up on the internet, and it told to great accuracy where the eclipse was going to pass through. In fact, they gave all sorts of details. It would be on July 22nd. It would be on so many time. It would last for 6 minutes. That is the longest in the century. It would start at a particular time, and that was there to the seconds, and so on and so forth. Okay. It also said it would be visible in Surat, Varanasi, Patna, and so on. And the map is this detailed. It had, that was the line of the central line of the eclipse, and these were all the cities that one could go to. I was in JNU at that time, and my daughter was 9 years old, and I felt that, this was an event I wanted to really share with her, so I said I'm going to take her to a city for looking at the eclipse. And, Patna is there, Sasaram, which is even closer, and Varanasi. I thought that, in the interest of a certain amount of safety, I'd rather not go here, and I elected to go to Varanasi, where there's a nice university and a good guest house and all that. Landed up there, sitting on Tulsi Ghat, 6 o'clock in the morning, waiting for the sun to rise so that the action could begin. And, so that was it. I mean, people in Patna had a much worse time. It was completely overcast. But when the eclipse started in Varanasi, everything else was determined exactly. The date, the time, the down to the very second. But just as the sun started, the moon covered the disk of the sun, a huge cloud and a huge set of clouds came and covered and it covered the entire eclipse. There you have contrasting the completely predictable natural phenomenon and, in a sense, the completely unpredictable other natural phenomenon, which is the weather. The story has a happier ending because this I happened to take at the time when the cloud was passing over. There was a huge gust of wind and everything got blown off, and I had the most wonderful view of the eclipse. So I did actually get to see the eclipse beautifully. But nothing was, this could have been completely covered up. So predicting the weather or the climate is a major challenge. And as, regardless of discipline, you can see that this is a point which is of great interest to us. We would like to know a lot of details about the weather, from the trivial aspect of whether you take an umbrella or not to work, to how much rainfall you can expect, or the details that you need to know to have to run a country, run an economy, what have you. Predicting something like the weather is extremely important and is difficult. Whereas predicting things like eclipses is important and certainly of great significance scientifically, but that is a done problem. It has been solved. Those can be addressed very well by the methods of modern science. Okay. And whereas the predicting the weather is still done to some extent empirically. We are getting much, much better at it, but it turns out that the difference between these two is that chaos or chaos theory has a lot more to say about predicting the weather. Okay, so the point is that it has a huge impact and it's very important for us to understand. So the question really boils down to something like this. Is there something about the nature of the system that makes one kind of phenomenon easy to understand or easy to predict and another kind of phenomenon much more difficult? Not that one is weather and one is eclipse, but is there something about the system itself? What makes a coin toss difficult to predict exactly? And why are other phenomena which we also see every day, why are those much easier for us to address? So the nature of this inherent unpredictability traces itself back to one rather simple one simple fact, and that is that many systems which are nonlinear, the importance of nonlinearity has not always been appreciated. And in the last 40, 50 years, it has increasingly become possible for us to do this in a very systematic way. Most of the physical laws that we are subject to are nonlinear. Most systems are nonlinear. Linearity is a rather simple and a very unusual behavior, as I'm just going to show you. And although most systems are nonlinear, we approximate them whether it is the first law that you learn, Hooke's law, or the laws of a pendulum, all these are approximations which are done because those are simple, and linear systems can be analyzed completely and exactly. We have an intuitive understanding of when you apply linear laws, whereas nonlinearity is somewhat more unfamiliar. This may be totally inessential, but let me just point out, in a linear world, and linearity applies, for example, in economics, to things like the price of gold. If you have a gram of gold for 2,800 rupees, then a kilogram is going to cost you 28 lakhs. That's it. Okay, no discounts, no nothing. Whereas if a kilogram of potatoes is 10 rupees, at the time that I wrote this slide it was, 1,000 kilograms is not going to be 10,000 rupees. Because you're going to negotiate, you're going to bargain, you're going to go for a volume discount or something like that. So this is a very simple example of nonlinearity. And since Valentine's Day is coming up, I might point out that the other aspect, if anyone's planning to buy a diamond, a 0.1 carat diamond is 9,000 rupees. And if you go with 90,000 rupees and ask for a 1 carat diamond, out, you're not going to get anything. So, okay, so this is sort of, I'm sorry, just as an example of, we are surrounded by nonlinear phenomena all the time. Okay? Some things are linear, those are relatively few, and they also exist up till a certain limit. Whereas the nonlinear with this mic as well. Now, this is the first kind of big question that you all are asked in high school or in junior college or whatever. And measuring the time of oscillation is the standard problem. Okay, so all of you know that T is equal to 1 over 2 pi under root L over some formula, that, right? But if you go to the lab and you try to do the experiment, and having done this, you go there and they'll tell you do it very, very carefully. Just do it, only move it slightly. So you do that, and now if you are a little more enthusiastic and you say, I want to do it like so, the instructor will come and say, don't do that, you'll get the wrong answer. Now, the point is that the pendulum is the pendulum. It's got to swing whatever it feels like. No, and if it so happens that it likes to do that, T is not 1 over 2 pi under root L over G. Okay, it is what it is. And the system goes away from being linear, it goes to being non-linear. And you can't just force the system to be linear because you want some answer to come out. Okay? All right. So this way. So if you do the mathematics, that's the kind of equation that you write in the linear approximation. And the nice thing about linear approximation is that you can get a solution, and the solution says that if I start at a particular, at some solution, this is one solution, and here is another solution, the difference between them is going to stay small. If the initial distance between them is small, then the difference between them will always stay small.